So last time, to quickly review, we talked about this idea of bubble pushing, which is, bring up the example, which is where if you have a circuit that's comprised entirely of CMOS negated gates, you can convert it to non-negated gates by starting from the output and pushing the bubbles backwards. So if you have a NAND gate, the inverted output could be transferred to the inputs, and then the gate would become an AND with inverted inputs because of De Morgan's law. Everyone see that? And then you continue pushing bubbles backwards, and then you can if you have a bubble on either end of a wire, then that would cancel out. Then we looked at some schematics, some circuit diagrams, and there was some, there was an example of this. In this case, they've laid out this thing where the inputs are connected to wires that run vertically, and then there are horizontal wires also that connect into these vertical wires, right? So in this case, I've got A, B, and C come down vertically, and then going horizontally is where I form each minterm by connecting each wire corresponding to an input or its negated form using these T junctions. And then those run into these AND gates, and then there's another vertical plane here for the OR gate that combines together the minterms. Does that make sense? So this is actually similar to the way real chips are laid out. If you look at an actual chip, there's these layers of what they call metal layers, which is the layers in which you can route wires. And they're layers because they're isolated with a layer of silicon dioxide in between them. And they give you the ability to connect together gates, essentially. But each layer alternates between vertical and horizontal wires. So it's kind of, this style of schematic sort of mirrors the actual layout of chips. We looked at this multiple output circuit. This was a priority circuit. Looked at how to implement that. And then there's this shorthand notation where you can reduce this table down to a smaller table by putting don't cares for some of the inputs in the table. Now, I mentioned last time that you have to be careful because a don't care, which is shown as an X here, a don't care on an input is different than a don't care on an output. If you have a don't care on an input, it means that you've basically compressed multiple rows into one row. So, like for example, if you have two don't cares, this one row is expanded, must be expanded into 4 rows when you implement the circuit, because you have to account for every combination of bits in those don't care slots. You guys with me? So what I'm saying is that these don't cares don't really help you much for minimizing circuits like output don't cares do. You guys with me? So this is more of a shorthand here. If you have don't cares in the output, it means that you don't care what that output value is, and that is something that you can take advantage of in a K-map to make the circuit simpler, right? So they're input don't cares and output don't cares. I'm emphasizing that because that's something that used to confuse me. Okay, also this idea of an X. What is an X? Well, an X, in the previous slide, they used X for don't care, but it can also mean contention, meaning that you have a bug in your circuit. You've got 2 or more gates that are trying to drive the same net, the same wire, the same physical, conductor, right? You guys with me? When I say drive, I mean set or output. In other words, you've got multiple gate outputs connected to the same connected wire, right? You can't have that. You don't want to have that unless there are tri-states on there to protect against this condition of double driving. Does that make sense to everyone? Not sure if I'm explaining that really well, but the idea is that, here's an example. So in this case, I've got two inverters and the outputs are connected. It's okay if the inputs are connected, but for each wire in your schematic, you can only have one, it can only be connected to one output, gate output. You guys with me? So contention means that I've got two gates fighting with each other over what the voltage value is of a wire. And that's really bad if you were to make a circuit that way, because it could lead to a short between power and ground. Because if one gate tries to set it to 1 and the other gate tries to set it to 0, then you've got a low impedance path between VDD and ground through the pull-up network of one gate and the pull-down network of another gate. Okay? So why am I mentioning this? Who cares? It's because when we get to the HDL chapter, when you design circuits in HDL, this comes up a lot. This is a very common bug that you'll see when you simulate a circuit. It's fairly easy to have a bug in your code that would lead to a bug in the circuit that causes this contention. And then we've got this floating value Z, which is when you have a tri-state gate that physically disconnects an output or disconnects one wire from another. And this is the symbol for it. E is the control, A is the input, Y is the output. So if E is 0, A is physically disconnected from Y. And whenever you have a wire that's not being driven by any gate, then it's floating. And it shows up as a Z when you design actual circuits and simulate them. You guys make sense? So what I'm trying to say is that when you do digital logic design, there's more than just 0 and 1. You've got the X and you got the Z. And the X is a little confusing because it could mean a don't care, it could mean a contention, or it can mean an undefined value. But so that part's a little ambiguous. But these are the different values. You guys with me? Okay. So then we talked about Carnot maps. I hope this is a review for I think everyone said that you covered this pretty well in 211. Carnot maps are an alternative way to take a set of min terms and convert them into a simplified form, simplified sum of products form, right? Does it work with max terms? Not directly. It's got to be min terms. It works with sum of products form. You guys with me? It doesn't really scale up beyond 6 input variables, though. So if you go to more than 6 variables, you have to use another method to minimize your circuit. But for small circuits, you can use these Carnot maps. The way that you build them is, well, you have some options. You can start with the regular old truth table, and you can transcribe this truth table into a Carnot map. That's pretty easy because a Carnot map is really just a truth table. The only difference is that it's laid out as instead of as a table, it's laid out sort of as a matrix. And you fill in, you put the outputs into the cells, which correspond to the output column in the truth table, and the inputs are given on the rows and columns, right? And then the only other difference is that the inputs are ordered strangely. It's notice 0001 101 0001 1110, right? Along the columns, and then the rows. If this were a 4-input instead of a 3-input Carnot map, the rows would be labeled the same way. You guys with me? So these are gray. These are called gray codes. This is the idea being that we only want to change one, change the value of one input as you change one row or change one column, or as you cross one row or cross one column, right? So you can take a truth table, and you can fill in the Carnot map by looking at each output, the output column, and for each one value in the output column, you could mark that one in the appropriate location in the Carnot map according to the input. So A, B, C, 0. So this is A and B are the headers of the columns, and C is the row header, so 0, 0, 0 represents ABC 0, and so you put a 1 there. Likewise, 0, 0, 1, ABC is 0, 0, 1. That's 0, 0, 1. You put a 1 there. And then the objective is that you're looking for implicates, which are groups of ones that you can circle and combine into a single product. You guys with me? So in this case, I can circle these two, and the objective there is, or the reason you do that is because if you circle these two ones, you can see it creates a sort of a rectangle that spans both values of C, meaning that C is redundant in this case. So this is equivalent to just y equals AB. Everyone with me? Now that's going from a truth table to a Carnot map. What if I don't have a truth table? What if I have a Boolean expression? Well, that's a little bit more difficult, but as long as the Boolean expression is in sum of products form, then you can also put that into a K-map. So let's say I have ABC again. So ABC 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. Okay, let's say I have y equals AB, right? Now I don't have C in there, I just have AB. So because it's just AB, this means that it doesn't matter what C is. C can be 0 or C can be 1. C is essentially an input don't care, right? So in this case, I can just go AB 1, 1, and then I can mark those both as 1s. You guys see that? All right. And then I might have like, let's say I have BC. Well, if I have BC, in this case, B is 1. B is not negated, so I'm looking for B to be 1, negated, complemented, right? B is not complemented inside this expression. So that corresponds to these two columns because B is 1 in both of those columns. And then you're looking for also when the C is 1, which represents these two cells, right? So that would be this guy and this guy. Make sense?
Why does it represent those ones again?
Because we want to find, basically the idea is we want to look for all the cells in which B is 1 and C is 1, right? So if you take each of those variables one at a time, we take B, we look for B being 1, right? So it's these two guys, right? These two columns are where B is 1, right? So that's two columns, right? And then it's this one row, right? So two columns, but just the one row where C is 1, right? So it would be those two guys. Make sense? And what happens if I had another one, like I could have also, like, let's say, not A, B. If I had not A, B there, I'm looking for the first two columns, because that's where A is 0. And, no, sorry, A, let me correct that. Not A, C. So I'm looking for the first two columns, not A. A is 0 in the first two columns, and I've got not A, right? And then C, again, is the second row, right? So that would be these two guys, right? Right? So in this case, is that right?
I was going to say you're only filling it out based on that equation down there, right?
Right, yeah. So if I have this, I can put the 1s in there. But see, now you might say, well, why are you doing this? I mean, why are you going from an expression where you already have implicates, right? You don't have min terms because they don't have all the literals. They don't have all the inputs. These are implicates. You're going from an expression with implicates to a truth table. That seems redundant. The whole reason to a Carnot map. The whole reason to use a Carnot map is to get to this state where we have implicates. Well, the reason I did this is because if you look at this, if I were to circle these two, then that means that y equals this first implicate is not A, because B is 0 and 1. So it's just not A is the consistent value here. And C, so this is not A, not A, C, that's right. Yeah, that's right. That's this guy. And then this one is what? What is this? This one is AB, right? Okay. So there's only 2. Now this is confusing. Why did I have 3 here and 2 here? Well, it turns out that that this one here was, this one, this circle here was here, but I didn't need it. It was redundant, right? So this is actually the consensus theorem from the list of theorems, the consensus one. This is consensus. This is one of those theorems. This is one of the ones that's really weird when you look at it. It's like, I don't get it. Like, why does that work? Well, if you put it on a Carnot map, you can figure it out. The reason why consensus works is because you start out with these three implicates, but one of them ends up becoming common amongst the other 2, so you can take it out, right? So that's just another example of the use of a Carnot map. Okay, skipping ahead here. So you can do 4 input Carnot maps. You can go all the way up to 6 input. I didn't show anything beyond 4 input because they don't do anything beyond a 4 input one in the textbook. So I don't have any examples of that. If you have don't cares in your Carnot map or in your truth table, you can use those to get bigger groupings. That make sense? But you don't have to. You just have to make sure that when you create groupings in your Carnot map, you have to cover all the ones. But you have an option. You don't have to cover all the don't cares. So if a don't care allows you to form a bigger group, then take advantage of it. So in this case, notice that they did not cover this don't care, which corresponds to 0, 1, 0, 1, right? So 0, 1, 0, 1, that's that guy right there. They didn't cover that. They didn't draw a circle over it. But they did draw a circle over these 4. And in fact, they used those 4 twice. They used it as part of this big one, this big 8-cell circle, and part of this one. And they used this guy for the 4 corners. Okay, you guys with me? I'm going, like I said, if you have any questions, stop me. I'm going through this fast because I know you guys have seen this before. Okay, multiplexer is a basic building block. It shows up in schematics quite a bit. If you ever look at any kind of digital logic schematic, like the ones that you've seen in 212, multiplexers are pretty common. You might be thinking, why? What's so special about these? What's the point? Multiplexers are fundamentally how you establish data paths in a CPU. So inside of a CPU, you guys know from 212 that from the programmer's perspective, the smallest unit of computation from the programmer's perspective is the instruction, right? You give a single instruction to a CPU, and it executes it, right? So a program is made up of a sequence of instructions. But from the programmer's perspective, each instruction is indivisible, right? It's like a single operation that's done by the CPU. But inside the CPU, once you get under the hood, each instruction is implemented using data paths by establishing pathways through different functional units and register files and registers on the CPU. And the way that all works is with multiplexers. You can use multiplexers to have multiple sources of data enter one place. Like, so for example, and you guys have seen this in 212. For example, when you do an add instruction, you can either add 2 registers together or you can add 1 register and a constant. Well, that second input has a multiplexer that allows you to choose whether you're adding the second operand or you're adding a register value or a constant as the second operand. You guys with me? So those are, these come up, these are very fundamental. Multiplexers can be implemented with gates or with tri-states. Usually it's not, usually however they're implemented is typically, not shown. It's abstracted away. You can also use multiplexers as a direct way to implement a truth table, just hardwire the inputs. Or alternatively, you can use a decoder. So a decoder is another common building block of digital logic. Why do we care? What are they used for? They're used for memory, generally. Decoders are the way that you have you have a memory that's organized as words, and there's multiple words. So in order to select which word you want to read or write in a memory, you use a decoder. Decoders do a binary to unary conversion, and as I mentioned last time, you can also use decoders to implement a logic function by basically just choosing which of the outputs of the decoders you want to fan into an OR gate, because each output would represent a possible min term. Right? So okay, so I think that's where we ended up last time. Okay, so then I think, let's see, we got the last topic of chapter 2 is timing. This is something that is probably new, because when you take digital logic 211 and 212, you assume that logic gates are instantaneous, right? You put an input into a gate, like an AND gate, you give it inputs and then it spits out an output. No one talks about how long it takes that gate to provide the output. But it's non-trivial, because gates are fundamentally capacitors. And they have capacitance and, of course, resistance in them, because there's resistance in everything, unless it's a superconductor. And so anytime you have capacitance and resistance, you have an RC circuit. And in order to charge up the capacitance, it's going to take whatever the resistance is times the capacitance in seconds, charge or discharge. So when I say charge, what am I talking about? Charge means I want a wire, and I want to transition a wire from a 0 to a 1. I have to charge it. So I have to physically move charge carriers to do that, and that takes time. And then if I want to discharge, it's the same thing. It takes time to discharge. So it takes time to drop a signal from 1 to 0. So if you look at a plot of the input and the output of a gate versus time, you'll see that if you look at the time at which you change an input versus when the corresponding change in the output happens, there's a difference, and that's the propagation delay of the gate. You guys with me? Do all gates have the same delay? No, depends on the gate. Also, it depends on what the gate is connected to, which is something they don't talk about in this book. But the gate delay can also be determined by how many other gate inputs it's driving, the capacitive load of its output. But in this class, you only have to worry about the fact that there's this propagation delay. There's also a contamination delay, which is the time before anything starts changing on the output. So if you have a gate and you change an input, there's a delay before anything happens, and then there's a period where the output is unstable, and then there's a time at which the output is stable. So the propagation delay is think of that as the worst case time it takes to update the results to their final value, update the outputs of a gate to its final value, whereas the contamination delay is when you see any change on the outputs of a gate. You guys with me? Make sense? Okay. Now, why do we care about, now propagation delay, that obviously determines the speed of your circuit. That's important to know. Why would we care about contamination delay? Generally speaking, it doesn't come up. It's not as relevant for performance analysis as propagation delay, but it will come up in the next chapter when we talk about sequential circuits, because contamination delay is a factor when you're trying to guarantee hold time for a sequential circuit, and we'll get to that in chapter 3. Okay, so I already talked about that. And then there's the critical path, which is the longest path through a circuit. And by longest, I mean the longest delay. That usually means the largest, the path in which you have to go through the most number of gates. So in this case, A and B have to go through 3 gates, whereas C only goes through 2 gates and D only goes through 1 gate. Make sense? Now, when you guys took 211, just to add a little context here, I think all of the circuits, or most of the circuits that you guys designed in 211, were 2-level circuits that were sum of products or product of sums. If you're doing a sum of products or a product of sums, which of course this book talks quite a bit about, those circuits always go through 2 gates. You always go through an AND gate and you go through an OR gate and you're done, right? Or if you're doing a CMOS version of it, you go through 2 NAND gates and you're done, right? However, real circuits very rarely are in the sum of products and product of sums form. And this is an example of one that's not. This is kind of an arbitrary circuit that's just a random assortment of gates connected together. This circuit doesn't follow any canonical form, right? So keep that in mind. Most circuits are like that. And the reason why is because sum of products is, the disadvantage of sum of products is that as you make a sum of product circuits bigger, the OR gate at the end gets bigger, right? The OR gate has to have 1 input for every minterm, right? Or for every implicate. So that's going to get to be a giant OR gate at some point, right? Let's say I might have a whole bunch of inputs into that OR gate. And in reality, real standard cell libraries, gate libraries, generally don't have many more than 3 input gates, 3 or 4 input gates at most. Because it's not really practical to make a gate with a lot of inputs. It becomes really slow. It's more, and it's also more cost effective to have a simpler standard cell library with just a small number of gates. So as a result, you have to trade off. You have to say, well, I can't go through 2 levels of gates, so I have to essentially apply the Boolean theorems to convert what could be done as a sum of products into another form in which you potentially will have to go through many, many gates before you get to the output. You guys with me? Okay. So now there's a side effect of this called glitches. The problem is that if you have a case like this, you may change an input. Every time you change an input, the output, the propagation delay of the circuit depends on how far away the input is from the output, how many gates it has to go through, right? You guys with me? And the other problem is that it could be the case that you can make a change where you change an input, and if it is fanned out to multiple points in the circuit, see, I don't think that other example had that, did it? No. See, this one, every input only went one place. See that? Right? But in reality, a lot of circuits have this fan out, like where you have an input and it goes to 2 places, right? In this case, B goes to this inverter and to this OR AND gate, right? Because I needed the B term, I needed the B input in multiple places. When that happens, and you change an input that's fanned out like that, B, it can cause a problem where the final gate that generates the output may receive its inputs out of order, right? So I'll change B, and the change the change in B will arrive at this input before it arrives at that input, right? Because I have to go through a longer path if I go through this inverter well, I will have to go through this inverter because it's connected to both. The B, an update in B will go through this path, and it will go through this path, but it'll arrive on the bottom path first. You guys with me? So, well, what's the big deal? Who cares? Well, let's look at an example here where if I have A is 0 and C is 1, right? So what that means is these are both AND gates. So if A is 0, I've got one AND gate with a 1 coming into it, right? And if C is 1, I've got this bottom AND gate with a 1 coming into it, right? So I got two AND gates that have one of its inputs being 1, meaning that the output of the AND gate is going to depend on the other input, right? Because I'm looking for a 1, 1 to put a true out, right? So if B is 1, then this AND gate will be true, right? And this AND gate will be putting out a false, right? Because B is inverted here, right? But then if I drop B, if I transition B from 1 to 0, it's going to flip this guy, and it's going to flip this guy. But the problem is that it's going to flip this one first, right? So this guy is going to go from 0 to 1. This guy is going to go from 1 to 0, right? Now the AND gate is going to be sitting here looking at these two guys, and it's going to see 0, 1 coming in originally before the change. Then I'm going to make the change, and this guy is going to go to 1, but he's going to be lagging behind because the extra delay that this inverter imposes on it, on its input, right? So what's going to happen is you're going to have 0 and 1. I change B. This guy's going to flip to 0 really fast before this top one flips to 1. Make sense? So the OR gate is going to be looking at originally 0 and 1. Then for a moment, it's going to see 0 and 0. And then eventually, it's going to see a 1, 0. Make sense? Well, the AND gate, if it sees 1, 0, and then 0, 0, and then 1, I'm sorry, it's going to see 0, 1, right, initially. Then it's going to see 0, 0. Well, the AND gate's like, oh, 0, 0, I should be low. But then once this top path catches up, it's going to see 1, 0, and it's going to go back high. So what's going to happen is all I do is change B. According to the truth table, changing B from 1 to 0 shouldn't make any difference. But what will end up happening is you'll see a glitch in the output, meaning that Y will go low for a very short amount of time, then come back up. It'll glitch. Make sense? So this also shows it, right? So you've got B is 1 to 0, it drops. This guy goes from 0 to 1. This guy goes from 1 to 0. So that should be a wash, right? I've got an AND gate. One of its inputs is going to go to 0. The other one's going to go to 1. Shouldn't make any difference, but it will because of the extra delay. So what will end up happening is if you look at the timing diagram, B is going to be high. It's going to drop. N2, which is this intermediate signal, will be the first to reflect that change because it's on a shorter path. So N2 will drop. But meanwhile, N1 is supposed to raise. It's supposed to rise. But N1 will rise after N2 drops. So there will be a period when there's a 0, 0 coming into the OR gate, which will cause this little glitch, a temporary disruption in Y. Make sense? OK, so the book actually has a pretty interesting rationale for why this happens. And they use a Carnot map to show why this happens. It turns out, and this is something I didn't even know. This is actually news to me. I didn't know you could do this. It turns out the reason why that happens is because if you look at the Carnot map and you convert that circuit to the Carnot map. So in other words, this circuit, now this is actually, this is I think a kind of contrived case because it just so happens that this circuit happens to be in a sum of products form, right? Which is, coincidence. So I think it's a little contrived. But because this circuit happens to be in a form, you might say, no, it's not. It's got these, well, these inverters just represent the complemented inputs, right? So we can look at this, we can analyze this circuit on a Carnot map because it's sum of products. If you do that, it's essentially just two implicates, these two guys, right? These represent the two inputs into the OR gate, these two groupings. It turns out that when you change B, so we've got 0, 1, 1 initially, right? Because A was 0, which puts it in these two columns. B was 1, which restricts it to this column. And C is 1, which puts it right here. So this cell of the Carnot map is where we start. When we drop B, when B transitions from a 1 to a 0, that moves us in the Carnot map over to here, because B goes from 1 to 0 and everything else stays the same. So notice what happened. We were in this implicate, we were in this group, Carnot map group, and we transitioned to this Carnot map group. And because we changed groups, it's going to cause a glitch, right? So the book suggests you can fix this by adding a third implicate, which is put a circle around these two ones. Now, you don't need to do that logically, but by doing that, it prevents you from being able to change only one input and having that change move you cross the boundary between two implicates, because you have this covering overlap between these two implicates, right? And so that requires that you add another AND gate to do that. And they say, well, that'll fix the glitch. Now, the problem is that that only works if you only change one input at a time. If you change two inputs at a time or more, then you've got a much harder problem to solve, because it would be easier to switch. By changing more than one input, it's going to be more difficult to ensure that in other words, by changing one input, essentially what that means is on the Carnot map, you can only move one square, is what that's meaning. But if you can change more than one input, you can move more than one square. And thus, this applies only because we're restricting this to a one input change at a time. Make sense? And of course, in real logic circuits, it's very common for more than one input to change. So in a lot of cases, it's very difficult to fix glitches. But do we care? Well, in the next chapter, we're going to talk about how, generally speaking, when you set up a data path in a chip, a large-scale circuit design, you have all your inputs into a logic circuit come from a register. And of course, because of that, by the way, when the register changes, you're going to change a lot of input bits, potentially all of them, right? Which makes glitches very common. But the output of the circuit is going to get captured into another register. And we're going to guarantee that that's not going to happen until the glitches are gone. The glitches have propagated out and stabilized. So in usually you don't care about glitches. It's usually not a problem in practice. But you'll see them, like when you design, even when you design an HDL and you simulate it, it'll show you the glitches. But if you wait long enough, the glitches will eventually stabilize. It's a transient behavior. Yes?
So if the gates are pretty much like capacitors,
Mm-hmm.
then how do that capacitors discharge quicker than they charge, like go to 0 quicker than they go to 1? Would that cause glitches?
Yeah, possibly, sure. Yeah. Yeah, the propagation delay will also be data dependent, depending on the rise time and the fall time could certainly be different. That's also the case because PMOSs are slower than NMOSs. So NMOSs, because NMOSs pull down, they're the ones that are responsible for dropping to 0, and they're faster than PMOSs. In real circuits, the PMOSs are so much slower than NMOSs that when you design, if this were a VLSI design class and we were actually drawing the circuit, we're drawing the layout, you always make the PMOSs at least twice the size of the NMOSs. So the designs look really weird because you've got the pull-up transistors are big and the pull-down transistors are small. And it looks kind of funny, but that's how you always design chips. That's one of the, at least in CMOS design, which is what everyone's been using for decades. Okay, so that's the end of chapter 2. Any questions? Any other questions? Okay, so again, the exam is just on chapters 1 and 2. I'm going to start chapter 3 now. Chapter 3, as I mentioned last time, is about sequential logic. Notice I changed the layout of my slides because before this I was taking the book slides and moving them into my own format, but that was introducing those bugs. Remember I pointed out a couple bugs in the slides, so I tried to change them and made them closer to the original form to try to clean them up, reduce the glitches in the slides. Anyway, the outputs, so combinational logic is what we talked about. That was the entire topic of chapter 2. The idea is that you design a circuit that has an output that's a function of the inputs, and that is all. Sequential logic adds memory. So that means that the output is no longer just an input, a function of the inputs, but it's also a function of the history of inputs. Now, what is the practical effect of that? Well, that makes circuits a lot harder to design because, think about it, if you look at a truth table for a combinational logic circuit grows exponentially with the number of inputs. But if you have a sequential logic circuit, it grows even more. It still grows exponentially, but it's not only because you've got the inputs that you have to consider, but also the state, which is the memory bits that are inside the circuit, right? The length of history that you can consider when evaluating the output. So there's this idea, I'm going to use this word state a lot. State just means the value of memory, right? So that word is going to come up constantly. We'll also talk about latches and flip-flops. I think you guys might have covered this a little bit in 211, but as I understand it, not very thoroughly. A latch and a flip-flop is the little primitive component that actually stores the memory in a sequential logic circuit. There's also registers come up. Registers are where you have multiple flip-flops in parallel that hold a multi-bit value. You guys probably, I'm sure you heard register a lot in 212. Register is a confusing word because it means two completely different things. If you program an assembly language, there's registers that you use to hold intermediate values, which are addressable locations in a program. But in a digital logic circuit, a register is just a multiple flip-flops. That's not addressable. It's just a value stored in a bank of flip-flops. So that term is a little confusing, but that'll come up a little bit later. And yeah, sequential logic is regular gates, and you add in these latches, flip-flops, or registers. Okay, so the basic building block is this idea. Now, latches and flip-flops are built from gates, believe it or not. There's nothing, but the way that you do it is you do this thing where you essentially introduce a cycle into a logic design. So if you're doing combinational logic design, you never want to do this. You don't want to put any cycles. Your circuit should be acyclical. But in a sequential logic element, notice that this inverter comes out, goes into this inverter comes out, goes into that inverter, this inverter comes out again, goes in that inverter, and there's this infinite loop in there, right? There's a cycle. The idea with this is that this becomes this particular layout. Now this isn't, just because you've got a cross-coupled logic circuit does not mean it'll hold memory. In order for it to hold memory, it has to be considered a bistable circuit. Bistable meaning that you can have at least, it can hold one of two states. You guys with me? The way that the idea is that if I can somehow inject a 1 or a 0 inside this loop, right? If I can somehow like stick it in there, right, it will stabilize. Because let's say I put a 0 in here for Q, 0 will come out, go into this inverter, become a 1, right? Then this 1 will come out and go in this inverter and become a 0, and it will stabilize. It will become a self-perpetuating loop. Make sense? But so if I can have a way to inject a 0 or 1 in there, it'll hold on to that value, right? Also, the nice thing about this is that I'll get Q. Q is the value that's stored in there. But I also get Q prime, or the complement of Q, Q bar, for free. And you might say, why do you need that? You might not need it. You might not connect it to anything. But you might need it because when you design combinational logic circuits, you often will need the complement of an input. And if you do, you don't even need to put in an inverter. You get it for free. It's just automatic. You get both versions of the bit that you're storing in the circuit. That's pretty cool. And again, you don't have to use them both. By the way, this is essentially an SRAM cell. SRAM is the type of memory that you use, that you build caches out of and register files and on-chip memory. And that's, to this day, that's how they do it. It's just 2 cross-coupled inverters. The only thing missing from this is a way to get something in, to inject a bit in, which in SRAM cells they use 2 transistors to do that, but we're not going to cover SRAM cells. Okay, I already talked about that. Okay, so here's something a little bit more complicated. Instead of inverters, let's use NOR gates. Why NOR gates? Well, a NOR gate is the thing about a NOR gate is that if I cross-couple NOR gates and then allow the user to provide the second input in each of those 2 NOR gates, a NOR gate, if a NOR gate gets a 1, if a NOR gate gets a 1 on one of its inputs, what does that mean? It means that it doesn't matter what the other input is, the output's 0, right? And it's a little, no, you have to think of, sorry, you have to think of an OR gate, right? An OR gate, if you put a 1 into an OR gate, the other input doesn't matter, right? Because you're going to get a 1 out. A NOR gate is the opposite, right? So a NOR gate is going to give you, if you put a 1 into a NOR gate, it's the same thing as an OR gate, except instead of you're guaranteeing a 0 is going to come out, right? Right. So the idea is that if I put a 1 into R, right, then Q is already determined, is definitely going to be a 0, right? So that 0 comes back around to this NOR gate, right? And then this NOR gate is going to have a 0 in it, meaning that a 0, I'm sorry, I screwed that up, didn't I? If I put a, let me scratch that. If R is a 0, right? Sorry, no, I had that right. No, if it's a 1, yeah, I'll definitely be getting a 0 out, right? Then you cross-couple that around, you get a 0 coming in. So I have a 0 coming into the bottom NOR gate, right? And what does that mean? Well, that means that the output is dependent on what the other input is, right? So if I put a, let's say I put a 0 in there, I'll have a 0, 0, right? In which case I'll get a 1 coming out, right? So this 1 is going to come up to this NOR gate, but it doesn't matter because I've already got another 1 in there. So I've already got that output there, right? But the thing is if I put a 0, 0 in, then if I put a 0, 0 in, what happens? If I put a 0 for R and a 0 for S, the 0 on this guy will mean that the other input is going to determine what comes out of there, right? So whatever was on here previously is going to is whatever was in here previously is going to essentially get inverted through this guy and come out as Q. Does that make sense? You guys following this?
Yes.
I think I've screwed this explanation up. So the idea is that in inverter, if you put, so the bottom line is, to describe it another way, if I put a 0, 0 for R and S, these inverters essentially become, these AND gates essentially become inverters, right? You guys with me? If I put a 0 into a NOR gate, then then I'll look at the other input and the output, and it just becomes an inverter. So this becomes a cross-coupled inverter. That's what I'm trying to say. You guys with me? So it ends up becoming equivalent to this, right? In other words, a 0, 0 will capture a value in here, and it will make it persist because these guys will essentially become inverters, right? However, if I put a 1 in for R, right, by putting a 1 in for R, I'm going to guarantee that the Q is going to become a 0 because if you have a NOR gate and you put a 1 into a NOR gate, you're guaranteeing the output is a 0, right? If this guy is a 0, and you come into here, and then I can, then this guy is going to be a 0, and then if I put a 1 in here, then I would put a 0 for S, right? And that way I'll have a 0 coming in here. I'll have a 1 coming out of here, a 0 going in here, and then I'll get a 1 and a 0. So I'll have a 0 coming out of here. So putting 1 for R and 0 for S assures that the output will be 1, 0.
That was 0, 1.
Oh, sorry, 0, 1. Yes, you're right. Thank you. Yeah, 0. That's right. Because 0, 0 for, 1, 0. I keep getting that mixed up. If you put, so the way to remember this, so I don't confuse you too badly, is R stands for reset and S stands for set. So if you put a 1 for R and a 0 for S, you're resetting it. So the Q is going to become 0. That's the way to remember this, right? Likewise, if you put a 0 for reset, R, and a 1 for set, then the Q will become 1. You'll set it, right? So there's a reset and there's a set. And of course, the Q prime is always the inverse of Q. Everyone with me? Make sense? So the one case I haven't covered yet is if you put a 1, 1 in it. A 1, 1 is an invalid input. You don't want to put a 1, 1 in because if you put a 1, 1, you guarantee that both outputs will be 0, right? Because you're putting a 1 in this guy, you're putting a 1 in this guy, and if you put a 1 into a NOR gate, you guarantee that the output is 0, right? You with me? So this is basically almost you could think of it like there's three modes you use this in. You have a reset mode, a set mode, and a hold mode, representing the inputs of 0, 1, 1, 0, and 0, 0, right? Make sense? Okay. All right, so moving forward here, yeah, so these slides show all that stuff. I should have showed those. Would have made it easier to describe. Okay, so another thing you can do is take an RS latch. You take an RS latch, and you can put these two AND gates here that basically just enforce the rule. But the way you do it is you have a clock, which is one of the inputs on both these AND gates. So if clock is 0, you force a 0, 0 input, meaning hold the value, right? If clock is 1, then this D will come in and it'll be a 0, 1 or 1, 0, right? Because you have not D coming into this AND gate and D coming in this AND gate, which will force R and S to be either 0, 1 or 1, 0 depending on the value of D. You guys with me? So you might say, what's the point of this? Well, the point is that these gates essentially force this thing to be used in the proper way, and it also creates this sort of this interface where if the clock is high, then whatever you put in as D gets passed directly as out. But the minute you drop clock down to 0, it will capture whatever was on the D input at the time you drop the clock, right? So by dropping the clock, by deasserting the clock, you capture a value inside there. At which point, it doesn't matter what you do with D, because whatever the previous value of D was when you captured it stays inside that latch.
Because of the delay, or? No, it's because the cross coupling. It's because it basically those front end gates, those front end AND gates enforces this usage where you have a 0, 0, which is capture, right? Why is it capture? Because it turns these guys into inverters, right? And the inverters are just a ring of two inverters, just constantly persist. They're stable, right? They're in constant agreement. It's like saying, oh, I'm going to invert you, and you're going to invert me. I'm going to invert you, you're going to invert me, and you just end up in this. You capture the data inside that inverter ring. If it's 0, 0. And so the 0, 0 is what you'll get whenever the clock is 0, because the two AND gates, you're using the AND gates to basically zero out S and R whenever clock is low. So by having clock low, you drop the gate and you capture whatever was previously in there, right? What do you mean by you saying you capture it?
So it's like I give it a D. As a user of this system, I will provide a D input. Now I can change that D to 0 or 1, and when I change D to 0 and 1, Q will also be a mirror. Not a mirror, but it'll match. It'll match my Q. My Q and D will be the same. D is my input, Q is my output, and so if D is 1, Q is 1, D is 0, Q is 0, but that's only while clock is high. If I lower clock, meaning set it to 0, then whatever my last D was, whatever the value of D was, the D input was, at the time I lowered the clock, that will stay in there. At which point, no matter what I do with D, I'll always have the old value of D coming out as Q. Does that make sense?
Why? Why is it still the old value? Because when you change D, does that really depend on the clock?
Well, it cuts off, if the clock is 0, basically by lowering clock, I cut D off from this circuit. It's almost like these AND gates cut it off. So once clock becomes 0, these R and S will always be 0.
Is that only if it's 1? If it's also 0, doesn't it open it up and it keeps going? Or
if what is also 0?
If clock is 0 and D is 0, doesn't that go through then the AND gates?
Well, technically, it might look like it does, but it's not. Yeah, you're right. I mean, if I've got a 0 stored in my latch, and I put a 0 in as D, and like maybe I didn't show you what clock. Maybe I hid clock. I'm not going to show you what clock is. All I'm going to show you is that D is 0 and Q is 0. You might think that clock is high, right? When in fact it's not. But that's only because there's just coincidentally my input matches the value stored internally in the latch. I think that's what you're asking, right? But that would just be a coincidence. In reality, Q is not 0 because D is 0. Q is 0 because D was 0 when I shut the clock down, right?
When you say shut it, okay, you say shut off, you mean you're changing it to 0, right?
Right.
Okay.
Yeah. In fact, so this truth table shows, when clock is 0, it doesn't matter what D is. It's a don't care, because Q will be the previous value of Q that was in there, that was in there previous to me shutting down the clock, right? If clock is 1, then D will be passed directly out to Q. So if D is 0, Q is 0. If D is 1, Q is 1, right? And then of course Q prime is the inverse of whatever Q is. So that's a latch. Turns out no one uses latches. Latches are difficult to design with. Instead, people use D flip-flops. D flip-flops are much more common than latches. D flip-flops are very similar to latches, but they have one difference is that instead of capturing Q when the clock is high, it captures Q on the rising edge of clock, or you can also alternatively make it the falling edge of clock. But the point is that instead of capturing Q whenever clock is high, in other words, instead of it being level sensitive to clock, if latches, whenever clock is high, you'll pass through Q to D, you put clock to low, and it'll capture whatever was there. A D flip-flop captures D on the edge of the clock. Now you might say, wait a second, what is the distinction between the edge of the clock and the level of the clock? Who cares? The difference is that the edge of a clock is an infinitesimally small period, really, really tiny. It's like, I always think of it as taking a snapshot. If you, like everyone talks about, you look at how long it takes, the propagation delays and clock periods and all that stuff are relatively long periods of time compared to the transition time of a signal. As it goes from 0 to 1, it usually goes pretty fast. Now, it's not a square wave. It's not, discrete. In reality, we know from chapter 1 that digital circuits are really analog circuits. But even so, when you go from 0 to 1, that transition time is generally pretty tiny. It's a few picoseconds. Or maybe, actually, femtoseconds. It's even less than a picosecond. You guys with me? It's usually a tenth. It's an order of magnitude less than like a clock cycle, right? You guys with me? So you can think of this like a camera shot. I always think of it as a snapshot, like a camera shutter. You have a D flip-flop, and the edge of the clock is like taking a picture of D. You snap a picture, and it like freezes D is really what you're doing. You're trying to sample D with the very short amount of time it takes to transition the clock from 0 to 1, and that's what locks it in. It's not locked in just because by virtue of the fact clock is high and the gate is open, the latch is open. But a flip-flop is a very small sample time, snapshot time. You guys with me? So that's the difference. But how do you build a flip-flop? Well, you build it with latches. You put two latches together, and you have one latch with a negated clock and the other latch with a non-negated clock, and you connect them into series. And so the idea with this is that these are both level-sensitive latches, and this one's looking for clock to be low. This one's looking for clock to be high. And because you've got them on opposite levels of the clock, it creates this effect when clock is low. You go through this guy. When clock is 1, you go through this guy. But there's a very small period of time when they're essentially both enabled. It's in that transitionary period, that rising edge. Make sense? So to summarize, we took, you start out with an SR latch, which is two cross-coupled NOR gates, which essentially are cross-coupled inverters, but there's that SR that allows you to get a bit inside of the cross-coupling, right, inside the loop. If you add some extra AND gates, you can make it an SR, you can make it a D latch, and if you put two D latches together, you can make a D flip-flop. And D flip-flops are the much more common sequential logic element. And that's what we'll mostly be assuming that we're using here as the basis of these circuits for the rest of the chapter. You guys with me? OK, any questions about that? OK, so now you have to get used to reading these timing diagrams because these come up quite a bit with these things. Basically, the idea is, and sometimes these little arrows kind of get confusing, but the idea is that whenever clock changes, whenever it rises, I should say, because I shouldn't say changes, because we're talking about changing only from 0 to 1. This is the rising edge, right? Now you can just as easily make a falling edge flip-flop, by the way. But I think every example in here is a rising edge. So now you might say, wait a second though, you've got a rising edge. Every clock cycle has if the clock is always alternating between 0 and 1, as clocks do, you're always going to have a rising edge and a falling edge, right? So what are you doing? Just ignoring the falling edge? Yeah, you pretty much just ignore one of the edges. So that way you can allow all the stuff that happens in your circuit happens on the rising edge. So you have from the rising edge to the next rising edge to do your work that you have to do within that cycle, right? So everything goes from rising edge to rising edge. So you can ignore the falling edge of the clock. Now that's hard to do initially because you're like, wait, it's there, you can see it. But you just look at the rising edges. So every time you have a rising edge of the clock, you expect there to be action on Q, right? You're gonna sample D and bring it into Q. So D is 0, but who cares it's 0 until there's a rising edge of the clock, which happens here. At that point, Q, let's see. Oh, this is actually comparing the output of a latch versus the flip-flop. So let's take a look at the flip-flop first. The flip-flop drops here. It drops in response to the clock, right? So you look at the rising edge of the clock, and there is a corresponding drop in Q. Why? Because D was 0 at the time that the clock went up. Now D changes here after the rising edge of the clock. So there's a sequence. The first thing that happens is, well, D is initialized as 0. Then clock goes high. That triggers the output of the flop to go low. Now notice what they did here. You see this double line that they put here? Right? The reason they did that is because they didn't know how the flip-flop was going to be initialized. So the flip-flop might have started out at 0. If it did, then actually Q wouldn't have changed at all. But if the flip-flop was a 1 before this timing diagram began, then we'll see a drop in Q after that first rising edge. You guys with me? So it's kind of ambiguous what it was, but we know that after the clock it's going to be 0, right? So then D goes up, Q ignores it because there's no rising edge until you get way over here and there's another rising edge on the next clock cycle, at which point Q goes high because that's what it happened to be at that rising edge, right? So the point of this diagram is that there was a rising edge here which guarantees that Q will be 0 after that rising edge, shortly after that rising edge, after whatever the delay of the flip-flop is. And then D goes high, which doesn't do anything until the next rising edge, in which case it'll cause the Q to go high. And then D goes low, goes high. Meanwhile, Q is ignoring it because by the time you get the next rising edge, D is high again. You guys with me? Okay, so on a latch, this line above it is the latch. In the latch version of this, the difference is that whenever a clock is high, D goes directly to Q. So in this case, clock is high, D goes high, Q goes high. Clock goes low, nothing happens. Clock goes high again, D goes low, Q goes low, D goes high, Q goes high. Then clock goes low, and then this change in D here does not affect Q, right? So after this clock is low, the latch is turned off. When the clock is high, the latch is turned on, right? Make sense? It takes a little while to get used to reading these. And
so the latch changes after every 2 changes of the clock, kind of?
no, the latch is so with the latch, you can pretty much only look at when clock is high to consider. Like if I were to ask you to reconstruct this diagram like on a test, all you would care about for the latch was when the clock is high.
Because whenever the clock is low, the latch doesn't change. It's just whatever it previously was, right? Does it make sense? So in other words, the latch is only allowed to change when clock is high. The flip-flop is only allowed to change on the rising edge of the clock, that instantaneous period when you're transitioning the clock from low to high. Make sense? OK, great. All right, well, that's all the time we have. If you have any questions between now and Monday, let me know.